Dr. Ingo Mierswa from RapidMiner. Dr. Ingo Mierswa is the founder and president of RapidMiner, a software company which makes real data science fast and simple. Ingo also has authored numerous award-winning publications about predictive analytics and big data. After multiple rounds of fundraising, the acquisition of Purdue, and supporting the positioning of RapidMiner with leading analyst firms like Gartner and Forrester, Ingo takes a lot of pride in bringing the world's best team to RapidMiner. He will be presenting a talk titled How to Ruin Your Business with Data Science and Machine Learning. Please join me in welcoming Ingo.
That is exciting. I mean, it's kind of late tonight already, and there's still a full house here. And I really like the fact that you're all coming just to learn how to ruin your business. That's a great idea. All right, so yeah, introduction happened already. I founded RapidMiner, I don't know, feels like a gazillion years ago. And the idea really was to make it so much simpler to do data science. But then, after some time, I realized there are some dangers connected to this. I mean, if you make things too simple, then all of a sudden the models might still be correct, but they might be used in the wrong way. So today we will discuss some of this, maybe the top 3 biggest mistakes people can do, especially rookies, but I see this over and over again, even for companies who are doing data science and machine learning already for quite some time. Okay, so before we get into the horrible stories of bad things, let's start with the positive one. Let's talk for a second on Amazon. Amazon's revenues, I think they'd be like 136 billion last year. That's quite nice, I take that. And some insiders believe that between 15 and 20% of this revenue is a direct result of the recommendation systems Amazon's using. So for cross-selling, upselling, you know all the stuff, like people who are interested in that book, also interested in some other books. Okay, and now of course it's no longer just books, but we know the story. So that is a pretty good example of how machine learning can work. And probably maybe even a better one would be Google AdWords. I mean, this is roughly like 65 billion in revenues, and basically 100% of them is just the matchmaking between content you're looking for and potentially products you might be interested to buy. So those are good examples. Here's another one which starts good, but unfortunately ended horrible. Who knows Tesco? It's a UK retailer, 10 people maybe. Okay, for the rest. Tesco tried to enter the US market, I think in 2013, 2014. Kind of failed with that, so apparently nobody knows. But in the UK, there have been a big deal. And part of the reason was because they started very early already investing into data infrastructure, data engineering, then into machine learning, loyalty programs, and making most of their data. So that's good. When they started, after a couple of years, 10, 15 years, they managed, as a direct result of machine learning, to increase their profits by 7x. For a company at that scale, that was a pretty significant improvement. But something went wrong. I mean, 3 things went wrong. First of all, entering the US market didn't really work well. Another thing which went wrong was some fishy accounting practice. We're not going to talk about this today, but that wasn't really great. The chairman needed to resign and everything, so that wasn't really good. But the main issue was really that consumers stopped buying at Tesco. Why? The models have been perfect. They've been working really well. Unfortunately, they've been misused. The models have been misused to such a large degree that consumers felt, holy cow, what is going on with my data? They know everything about us. They really, literally sent me advertisement which is kind of perfect. People freaked out, the sentiment turned, and they've been looking for competition. So that wasn't really good. All 3 things together, I'm not saying this is the end of Tesco, but I mean, they're still around, but that wasn't really a great success story for machine learning. So what is the difference? What is the difference between cases like Amazon or Google where things went really well, and there's hundreds and thousands more of other companies, and then situations like a Tesco where things didn't work out so well? So, in order to answer this question, that will be the question for the rest of the presentation today, we have to do one thing. We have to analyze some evidence, especially alien behavior. I mean, that's kind of obvious. And if you think now, okay, this lady and this guy in front of the stage here is completely crazy, you are right, but please bear with me. I hope you will enjoy it. Let's have a look at the formula. This is the total number of alien UFO sightings per year since 1963. And just in case you're not noticing yourself that something changed, look at this orange dot here. In 1993, and all of a sudden, the number of UFO sightings has dramatically increased. Anybody in the audience with any idea what might have happened in 1993? Please. Camcorders. A brilliant idea. It may be correct, but not what I think is the true reason.
They actually arrived.
They actually arrived. Of course they did. You are right. Of course they did, because the data shows it. Please. More Photoshop. I'm not sure how long Photoshop is around. That might also contribute, but there's another reason.
The internet.
The internet, that is a brilliant idea. The internet was invented in 1962. You probably mean the World Wide Web. It was invented in 1996, so 3 years later. And actually, that might be the reason for another increase in 96, 97. Look, come on guys, I am in LA, close to Hollywood, you should know. The X-Files, that is perfect. The X-Files, the cult TV series The X-Files, premiered in September 1993. And had more than 5 million viewers at its peak, more than 20 million viewers. That's more than 10% of the US population. And I think Nielsen got it actually wrong, because Nielsen only counted human viewership. But of course, aliens are a natural extension to the target audience. Of course, all the aliens like saw what's going on here on Earth and thought like, holy cow, that's exciting. They show a TV series about us. Let's go down there and let's watch the X-Files together with human beings, because aliens are huge fans of the X-Files. It's in the data. Another one. This is the number of UFO sightings separated or grouped by hour and day. Yellow or orange means a lot of UFO sightings, blue, not so many. And look at that. We just heard about aliens being social beings. Okay, coming onto Earth, watching the X-Files together with us. I don't think it's coincidence that actually most alien sightings happen during the peak hour for fraternity parties. So I think personally, because they are so social being, those aliens come to Earth to party with us. Actually, if you think a little bit about this, that's actually crazy, because they're coming from planets, from galaxies light years away, I assume, from the different suns and planets. There is no 7-day-a-week, 24-hour-per-day schedule there. I mean, why should they adapt? Again, because they are social beings. They come to Earth, they do during the day whatever aliens doing during the day, probably they work, and then they party hard. So aliens, social beings, work hard, party hard, totally. And finally, and this is the most important one, here is the average number of UFO sightings per week. Okay, you see where this is going to. I mean, honestly, since we know aliens are social beings, I think my German friend Roland Emmerich, he got it completely wrong when he was creating Independence Day. I mean, he was showing aliens coming to Earth to destroy the White House and kill humanity. That's completely off. I mean, we saw it already before they're social beings. They're not coming to Earth to kill us all. No, they're coming to Earth to actually celebrate with us, because aliens, they are true patriots and they love fireworks. Okay, so you have the message here. 3 times you look at data, and of course it's obviously wrong. I hope at least it's obviously wrong. But still, I mean, is it? I can look at this data and I can draw those conclusions, and there is actually no way really to prove me wrong. I mean, you can now analyze a bit more, but just with this data, I can get to those conclusions. And this leads, of course, to one of the biggest problems we still have. It's the good old correlations, just things happen at the same time, or together, versus causation. We believe things are actually caused by each other. So that is the good old problem. We still run into this. I actually run into this kind of once per week. But that's only the probably most common problem. Another one, and I will show you a couple of demonstrations for this, is even if you create a machine learning model which you can use to predict the future, if you validate this model in the wrong way, you think this model works perfectly fine, and the production later, you will realize it doesn't. And that's a huge problem. I think it's maybe even bigger than the first one. And we saw before that only maybe 50% of all big data products end up in production. The same number is roughly true for machine learning products. But those 50%, they better are correct. Because otherwise you automate decisions left and right and will end up in big trouble. And then the last thing, this was something I was doing wrong my whole life. I mean, I do machine learning data science for 17 years now. It wasn't, of course, called machine learning data science. Well, it was called machine learning. It wasn't called data science back then. But people just focus way too much on algorithms. Ooh, great lucid trees. Let's use them. Yeah, sure, let's use them. But let's not forget about the data. Deep learning, whatever is the latest hype, put them into your toolbox. But don't think just because it's a new algorithm, I mean, deep learning is not that new, but because it's a new algorithm, this is the silver bullet solving everything. Use your brain, it's going to be a really good solution. Anyway, so we go into those three problems quickly, and let's start with number one, this confusion between correlation and causation. We already saw the examples around the airlines. Here's another one which is kind of dangerous. Some of you might know it actually. In Chicago, in 2002, 2003, there was a nice study, and this study has shown that if there are more books in a home, that the children living in this home have a higher chance to get better grades in school and do their exams. Okay, that kind of makes sense. I mean, like, if you have a lot of books, you read a lot, you're curious, you learn more, you probably are better at school then. I mean, makes sense. And now something happens, and that happens a little bit too often. The governor of Illinois, a gentleman called Blagojevich, he was later on in a couple of scandals. That's not the topic for today. But back then, without knowing more than the scandals, I actually have to applaud. He heard about this research, and they came up with a brilliant plan. They said, okay, if there's more books, children are better in school. If they're better in school, they will get better jobs. Better jobs pays more money. That means more tax money. That's a very, very, very long-term investment, but it will pay off for the state. So let's do the following. Let's give every child one book per month between the birth and the moment in time they enter kindergarten. The total cost of this plan will be $26 million per year. But hey, again, it will pay off in tax money down the road. Brilliant idea. Unfortunately, there was a tiny problem. Because there was another study which then showed that it doesn't even matter if the children actually ever read the books or not. The exams have been coming out with better grades. So the people looked into this now and thought, like, wait a second, what about our whole idea about reading more books makes you smarter, better in school, better jobs? Well, this whole thing breaks down again. And it did break down. And we still don't know really for sure what the true reason is, but most researchers believe it's not about the books at all. It's about the environment created by the parents. If the parents actually invest more into books, that means they value knowledge a little bit higher, and they're more likely that they, in general, create a better environment for learning. That is the true reason, not just the existence of books. Okay, so that was apparently not such a great plan, but if somebody would have implemented this, that would have been a $26 million investment per year. So now, let's do something together. I would actually like now to do a little bit of data science with you guys, on a data set probably 80% of this room know. And I would like to see in this room of, I don't know, 100 people, how likely is it actually that you will do the same, stupid mistake the government did, or we before did with the aliens? Let's see. Okay. So this red minor, that's not the point. I mean, I could show the same thing with R, Python, or whatever. But the idea here is that we will build analytical processes, and since I don't have enough time today to actually build everything from scratch, I will actually load some of those processes, explain them to you, and then we will analyze some data together. Okay? So the idea here is open this one here. The idea here is that this process actually loads a data set, the Titanic data. Who knows the Titanic data? for 80%, but even better. Okay, wait, who knows the movie Titanic? Good. Okay, so, by the way, like half of the men don't know, I never saw it. Right. I saw it twice, by the way. So anyway, so the Titanic data set, let's have a look. So the first
like Celine Dion though?
Sorry, once again?
But do you like Celine Dion?
I just didn't get it, but that's the stuff. Anyway, so the first operator here loads the data set, and we will look into this. And then the second operator here is a cross-validation for validating the model. And the model we are building is, in fact, a gradient boosted tree here. And well, for those of you who know how cross-validation works, we train the model on 90% and apply the model on the remaining 10%. We do this for all the 10 parts of the 10-fold cross-validation, calculate the average, yada, 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 and end up with an average estimation of our predictive accuracy. Okay, so first let's run this process. I put a breakpoint after the data loading. So here's the data. It's 1,309 passengers on the Titanic. We have all the names here. We have one column which we want to predict. This is the target. The survived column. So we would like to predict who survived the accident and who did not. So for example, Mr. Andrews here didn't survive, although he was a first-class passenger. Whoever knows the movie, of course, things now, well, people in first and second class have a higher likelihood of survival. Let's later check if that's actually true. 39 years old. He was actually traveling alone from Southampton. Okay. And then, of course, we have the whole data set. Now I run this whole thing.
The software I use to build.
Sorry, I'm firing up Spark and it's going back one, but that's not the point.
Digital signal.
Well, there's 100. Next time, faster. I should have been
Basically,
before. Okay, here we go.
different skin. It's an audio photo.
97% accuracy. 97% accuracy with a gradient boosted tree model.
I can't. Yeah.
That's pretty good. I would say that's really good. That's surprisingly good. That's suspiciously good. That's way too good. How can we, I mean, honestly think about this, how could we predict, almost in a perfect fashion here, if people would survive the Titanic accident or not? I mean, there was pure chaos on board of the Titanic. Any ideas? Women survived, men didn't. Yeah, kind of, but that's not the reason why we are so good. You will see a little later, in roughly 2 minutes, that actually is the most important influence factor for survival. Because, I mean, I can say to myself, I see it even today, I learned about women and children first, and I'm screwed. And that was true for all the men on board. That is correct. But that's not all. Even if you know that, our model will be only roughly 80-85% accurate. No, there's another reason. No overfitting here. I mean, I did a proper cross-validation. We will talk about correct validation a little bit later. So if overfitting would have occurred during this, my cross-validation should actually not show that good result. But that's often the reason. But not here. The what? Like the passenger class, you mean? Like first class, second, third? It's the second most important influence factor. No, there was something else. And of course, that was a little unfair. The what? The boat they got on. Well, like something like a lifeboat? Yeah. The freaking lifeboat was still in the data set. Nobody noticed. This whole thing only had 7 columns and nobody noticed that the lifeboat was still in the data set. Of course, if you make it a lifeboat, you will survive. If you don't make it a lifeboat, you're pretty much screwed. I bet it's a great boosted trees. I took them out through all the 20 models, and of course, I would do it typically, but I go through all the 20 models, and guess what? Lifeboat is always on top of the decision trees. That makes it pretty simple. But this is a problem because the fact if you make it on a lifeboat and the fact that you survive this whole accident, that's highly correlated, obviously. Sometimes that's okay. Sometimes you want actually to keep those highly correlated estimates in. But in this case, it's not okay. And the reason why this is not okay in this case is because after the Titanic was hitting the iceberg, it's not too late for me to do anything. I mean, consider, while I was boarding the boat, somebody comes to me and says like, ooh, Mr. Mierswa, yeah, you're male and you booked a third-class ticket. Just in case we hit an iceberg, you're dead. So I still can do something, but after I made it on the board, I mean it's 1912 or 14, no, 1912, after I actually enter the boat and we are in the middle of the freaking Atlantic, there is no way that can do anything. There was no mobile, I couldn't call a helicopter, I'm dead. So the point really is, here the correlation is a problem because the piece of information, if I made it on the lifeboat or not, it's not just correlated with the label, it's also the moment I know if I made it on the lifeboat or not, I can't do anything. And for that reason, I need to take it out. So if I go, for example, so first of all, take a look at the correlations. So here we go. I mean, it's pretty simple. You calculate the correlations. Aha, surprise, surprise, survived and lifeboat are highly correlated. Well, let's just take it out. And if you take it out, so this operator now just removes this column, so now it's gone. If you do now the same thing, now we end up with roughly 80% accuracy. And actually our model here looks much better, and in fact, as predicted, the gender is the most important one. And that's okay because I'm not changing my gender. I mean, well, today. Anyway, because this whole thing is 1912. So, back to the presentation. Sure, we won't make it. I hope still it's okay. Anyway, so here's what you can do to avoid this problem. It's actually pretty simple. Before you start modeling, look at the correlations and then think. And that is exactly why I don't believe in fully automated data science as of today. Why? Because a fully automated machine learning, including data preprocessing, whatever solution, where you just upload the data, press a red button, and say, like, go and model for me, won't think for you. The only decision this fully automated system could do is, oh, that's great, I know so the lifeboat information, let's keep it in, my predictions are so much better now. And that is actually a problem even human beings are often, this mistake is done by human beings and equally often. I mean, think about this, we just gave away a really interesting piece of information and the quality of our model dropped from 97 to 80%. That hurts. I mean, most human beings would still say, like, well, I can't go to my boss with that model now, but the 97% looks pretty awesome. Yeah, but it would still be the wrong thing to use it. But if you automate it, or if you use an automated optimization there, you have to keep it in, or it would keep it in, and you will run into a disaster. Because, well, here we have 10 columns, that's easy. Try this on some sensor data from some machines and some production processes with thousands of columns, and we talk again. If you as human beings can still detect if you should or should not have this piece of information. So whenever there is a piece of information which is not available to you at the point of prediction, take it out, please. Everything else, sure recipe for disaster. Okay, the next thing is the wrong model validation. I would like to get through this one here because it's kind of like an interesting topic as well. Sorry. You can see the screen. Good. So first of all, never ever use the training error for anything, but we don't have the time to actually go into this one. But let's have a look here. This is a different data set. It's the sonar data set. It's kind of a military application. You have some frequency spectrum, and you would like to detect if what you're measuring is a rock or a mine. I, as a sailor, would care if there's something which looks like a rock or a mine. I'm not going there. But I guess for military ships, that might be an important piece of information. So we are going to use the K nearest neighbor classifier. Because why not? So it's inside here. In the cross-validation, same setup than before. But we all know, since K nearest neighbors is using a similarity measure or a distance measure, we need to normalize the data before we actually model it. Here's a small little hint. Oh yeah, sure. Let's add the normalization here, and let's run this whole thing. So here's the data set. Let's quickly visualize a little bit. So the goal is to distinguish between the blue and the red lines. That seems to be easy. Even here, there are some areas where there is actually some difference between the two classes, so maybe it's possible. So let's run this whole thing, and we'll see we get an accuracy of 86.6%. Just remember this number for half a second. 86.6%. What did we do wrong? And I give you a hint, because I'm running out of time. I only did one thing. So what did I do wrong? I normalize, right. Normalization is not the mistake because, well, it is still a distance-based method. I should normalize. But what did I do? I put it into the wrong position. Like, wait, every data science enthusiast in this room thinks like, but where else to put it? Well, not before the cross-validation, but inside of the cross-validation. Why? Because the normalization looks at the complete data set at the same time. It becomes kind of a part of the training process. That's why I personally would never recommend to separate data engineering from machine learning. It's still the same thing. The second you put the normalization before the cross-validation, you start cheating because you're leaking information about the distribution of your data into the complete transformation of the data set. And that is information you shouldn't have. If you put it inside of the cross-validation like here, you only take the information from the training data and apply the same normalization transformation on the test data. And now if I run this whole thing, I end up at 85.6. So before we had 86.6. 1%, who cares? Well, I do. The problem is, it's not just this 1%, it's actually 1% here, and another 3% if you do this wrong with parameter optimization, another 5% if you do this wrong with feature selection, another 1% if you do it with a different type of filtering, for example, look into this complete data, and it adds up. And sooner or later, you will end up with another 97% perfect model, and just then, that's the moment in time they realize, oh, that looks great, let's go into production. But in production, you will end up with the 85% we see here. 12% less, and that might cost you a lot of money. So just quickly back here, and before I wrap. So how can this ruin you? Well, if you actually take a model and you think, if you take a model, let's say for customer churn here, and you think that your model is so good that you could reduce the churn rate by 20%. Let's say you have 200 billion in churn before, 20% is 40 million. Great, but you're not getting this reduction for free. You need to do something. Make a better offer, give a discount. So you need to pay something. Let's say you have costs of 20 million. So if this model now was incorrectly validated, and in practice later on, after you go into production, it turns out that's not 20% reduction, but only 5%, meaning 10 million revenue savings. You turn the 20 million gain into a 10 million loss, and that means you as a data scientist are looking for a new job. That's not good. And I've seen this, even at that scale, happening 10, 15 times over the last 5 years. So that's why not just the focus should be on model building, but actually also on correct validation. And unfortunately, for our Python, if you program it yourself on all this whole stuff, you will actually end up validating your models in the wrong way. And if you would like to learn more about that, I wrote a complete white paper, 15 pages, thousands of examples. Let me know. Okay, so anyway, that's what we're doing. I think I need to wrap, kind of like 1 minute, 2 minutes, brilliant. So I started with this whole thing, we want to do real data science fast and simple. And we started out with the statement, hey, let's do data science fast and simple. Only a couple of years in, I realized that's not good enough. If you oversimplify things and if you sacrifice doing it in the correct way, actually there is no value in your models whatsoever. So let's not compromise on the quality of results or completeness, but let's still do our best to make data scientists more productive and make things simpler so that more people can do data science. Yada yada yada, we are the best, running out of time. Gartner loves us, Leader, Forrester loves us, Leader, Kenny Nuggets loves us, #1 open source data platform. In short, we're just great. So anyway, so what can you do in the future? Check for correlations before you actually start modeling is #1. #2, always cross-validate your models. Important, but also cross-validate your data preparation, and that's what most people are not doing. That's why there can't be a full separation between data engineering and machine learning. That's super dangerous. And the last thing is, I didn't talk about this, or I only alluded to this, use a little bit of common sense, use your brains, do some feature engineering before you start with the fancy models. Sometimes good feature engineering with a simpler model actually outperforms the more complex ones. And of course, please choose Rapidminer for all of this. One question, more questions? One question, okay. wanted to.
Do you correlate alcohol consumption with all the alien data you saw?
Yes. No, but talking about alcohol consumption, this is okay. No, that goes away. One of the best analyses I ever did in my life, and you should check it out. Everybody here is look at the data about accidents in the United States, and there's a huge database online, and you see the impact of alcohol. So there was a lot of surprises around that. So please, this is one of the best data sets I've ever analyzed. By the way, if you're riding a motorbike, don't even bother wearing a helmet because it doesn't make a difference. You don't die. No matter what. I didn't say that. Don't quote me on this. Oh, anyway, thank you very much.